Hi everyone. Thanks for joining us again at the ZX seminar. Today we have Matthew Sutcliffe talking about two papers, for instance, which is about speeding up classical simulation of quantum circuits via parametric analysis and weight propagation in ZX calculus. So Matthew, please take it away.
Yes, hello. So I'm going to be covering these two papers, as John just mentioned. If you're based in Oxford and you were at the quantum launch toggle last week, then you could probably get a tea and come back in half an hour, because I talked about the first one this time last week. And then the second one, well, both of these are pertaining to classical simulation, just kind of two different approaches. So one is based on how we can parameterize the rewrite rules so that we can reduce the redundancy in the work. So if we have circuits that are kind of simplifying in the same way, we can simplify them as one. And then the second paper is how we can use a simple cutting decomposition together with some basic heuristics to sort of efficiently decompose. So we'll get to that as well. And I'll just do the first one for the first half and the second one in the second half, just keep it kind of nice order. So obviously this is the ZX seminar, so everyone's very familiar with ZX calculus. But very briefly, I'm going to express my quantum circuits quite often just in this generic gauge form. And then, of course, we have the rewrite rules. So I'm sure you're all very familiar with these, but we can apply these to simplify any ZX diagram. And then we have the derived rules and the scalar relations. And then what we would normally do is plug the inputs and outputs of a circuit. And if this is a Clifford circuit, then this would just reduce fully to a scalar. And then taking the square of that scalar would tell us the probability of getting this particular output bit string given this input bit string for this particular circuit. So this is essentially strong classical simulation. And if we're dealing with Clifford+T circuits, so we have these pi/4 phases involved, then it will not simplify fully. We will end up with some graph that looks like this. And then we'll have to rely on a decomposition. So for instance, this is the BSS decomposition, which converts a set of 6 T-spiders to a sum of 7 stabilizer terms. So what this means is that we reduce our graph, it'll end up with something like this, and this will reduce into a big sum of terms, of Clifford terms. And obviously this is exponential, so it's going to grow quite rapidly with the number of T-gates. And then since each of these are now Clifford, we can reduce these and sum them up, and that gives us the amplitude of the initial graph. So very broadly speaking, that's how we would strongly classically simulate a Clifford-T quantum circuit. And then we want to consider marginal probabilities. So this is to say that suppose we want to know the probability that the first output is 0, the second output is 1, and we don't really care what the other two outputs are. Then we can do this like this, just by summing over all the possible graphs for those outputs, or we can do it by composing against its own adjoint. So there's 2 ways of doing that. And then lastly, we want to look at weak classical simulation. So this is to kind of emulate what a quantum computer would do. So to give some input bit string and try and probabilistically get some output bit string. So how this works is we apply marginal probability for the first qubit to see what's the probability this would be 0. And then say it's 0.4, then we probabilistically set that qubit to be 0 with probability of 40%. And then we marginally compute the next qubit and so on. And so we have the whole bit string. Yeah, so I'm going to consider a very simple example here where we're just looking at 4 qubits. And the bottom 2 are the ones we don't really care about. So this would be something like this if we express this out in full in the sum form. And how we would normally do this is we would sort of treat these independently. So the first one, we would simplify and decompose into a big sum of terms. And then calculate that and square it, and then that gives us this amplitude, and then we repeat this whole work again for the next one, and the next one, and the next one. But kind of the idea of this first paper is that a lot of this work is kind of repeating itself, so can we remove this redundancy? So we'll just take this initial graph, which has it parameterized, and we'll work with that. So yeah, this is what I was just saying, where we're doing this big work of simplifying and decomposing 2 to the n times. And we can see here that I've got my parameterized outputs over here, A and B. And regardless of what A and B are, we're going to be doing some simplifications that are the same in all of these graphs. So for instance, in all these graphs, we can fuse these three T gates and we can fuse these two pi over 2 gates. So we're kind of doing this same simplification on all the graphs, one after the other. So instead, if we keep it parameterized and reduce that as 1, then that saves us a lot of work. But of course, there are going to be cases where these parameters A and B, their actual value will matter. So we're going to consider how the rewrite rules could be parameterized to have kind of a general strategy. So these are the rewrite rules, which we outlined at the start. We'll just kind of go through some of these one by one and see how we can parameterize them. So firstly, we'll start with fusion. So if we're fusing two numerical phases, obviously that's fine. We just sum them up. If we have a parameter in there, then we can just keep that as is. We'll fuse it into one vertex, and that vertex will have a phase which will be given by some parameter plus some constant. And likewise, if we have two parameters, we can just keep that as the sum of two parameters when we fuse to one vertex. So in general, then we have these mixed states, which would be some Boolean parameter plus some constant. And when we sum these together, we just sum the parameterized parts and the constant parts. So we end up with some string of summed parameters plus some constant. And since these parameters are Boolean, then if we're adding like ones together, then so for instance, here we have b pi in both, we end up with 2b pi. That's going to be 0 regardless of whether b is 1 or 0, because either it's 0 or 2 pi, and 2 pi is 0, which implies that these plus signs are actually XOR strings, which means that the format for our phases, every phase we can express in this format. So we have some XOR string of Boolean parameters times pi, plus some Clifford+T constant. Yeah, so fusion rule, we can generalize that. That's not a problem for us. And then we look, a couple of these other rules don't actually change the phase or don't involve any particular phases, so we can kind of tick those out. We don't have to worry about those. And then we'll consider state copy. So we'll just remember that we have these two parts. The constant part, we know it's either going to be 0 or pi. So we don't know what that value is, but we know that it's in that domain of 0 or pi. Because we're not evaluating these parameters until the end. So that's the point. And then the constant part, we can just write a C for now. And so given the format that we have here, then we know that the phase is either C or C plus pi. It's always in this domain separated by pi. So if we express this as this kind of wheel of phases, they're always opposite ends of each other. So if the constant part is pi over 4, then we know that this phase could be pi over 4, or it could be 5 pi over 4. If the constant part is pi over 2, then we know that the phase could be pi over 2 or pi over 2 plus pi, which is minus pi over 2. So if we're considering something that kind of matches the structure of this rule, we can just ask ourselves, does this rule apply? So this green part, the Z spider, does this map to alpha? Which alpha is just some arbitrary phase, so that's always going to be true. And we care more about this X spider. So we're saying, does this equal A pi for this rule to be relevant? And we only have to consider the constant part. So if the constant part is anything but 0 or pi, then we know it doesn't apply. But if the constant part is 0 or pi, then we know the rule does apply. And then to generalize this, very straightforward, we just exchange this Boolean parameter, A, with our XOR string of parameters that we said we were going to have, capital A. And then we'll come back to these last two rules because they were a little bit problematic, and we'll move on to the derived rules.
I'm sorry, Matthew.
Yeah.
Are we ignoring scalars for now?
Whereby?
Because in this copy rule, like when you get this e to the I a alpha, right, where like a is multiplied by this alpha expression, and then if a is parametric, then a times alpha now is like of a different formula you were discussing before, right? That you get, like you were saying, the parameters is only like 0 or pi, but then when you multiply by alpha and the scalars, and then you can get something more complicated in the scalar.
Well, A here will either be 0 or 1, right? So we would just keep this as just a parameterized string, so we're not kind of evaluating this yet. So this would literally just be subbing in our string of parameters into A here. But we'll get on to evaluating it at the end. Yeah.
Okay, good.
So for local complementation, then we need the phase to be plus or minus pi over 2. So if the constant part is anything but plus or minus pi over 2, then we know it doesn't apply. And we can generalize this like so. So imagine, let's talk through this now. Imagine that this constant part here is plus pi over 2, and this bit string is 0. Then we would just have this normal scalar that we have at the top, which with this e to the plus I pi over 4. But if this string of Boolean parameters were to be evaluated to 1, then this phase would go from being plus pi over 2 to minus pi over 2, which means we would want to change from the plus on this scalar to the minus part. And to do that, we can just essentially add this extra scalar, which says if this Boolean string is 1, then we just add this minus e to the I pi over 2 term. So that essentially just flips this sign. So there's just an extra little step to consider on this rule, but generally it's fairly straightforward to generalize this. And we can see the scalar here has 2 components, has a constant part and a parameterized part. So the constant part can just be absorbed into some global scalar. And the parameterized part, we just want to keep track of these. So we'll just have a big list of these as we go along. And these will just be kept parameterized for now. And so we have one more rule to consider, and this one is fairly straightforwardly. We replace the Boolean parameters with our actual strings of Boolean parameters. And then likewise with the scalar relations. So back to these two finicky rules. If we look at pi commutation, let's see why this is a problem. So far, all the rules have mapped some phase, either just adding phases together, or it's been removed and pushed into a scalar, or we've added pi or some parameter string plus pi. But this rule asks us to flip the phase, flip the sign. So if we want to express this just in terms of adding some kind of phase, then we'll see that this becomes quite problematic. So first of all, we want to change this to capital A. So we're saying it's a bit string. And we'll kind of break this down into 4 distinct rules. So if we consider the constant part of alpha to be 0 or pi, then if A is 0, it always maps to itself. And if A is 1, we're flipping the sign. So if we're flipping 0 to minus 0, that doesn't change. And we're flipping pi to minus pi, that also doesn't change. So in other words, if the constant part of alpha is 0 or pi, then the change we make to this phase is always just mapping to itself. It doesn't make any change. So we can write this rule like this. Hopefully that makes sense. And then we want to consider the plus or minus pi over 2 constants. So if the constant part is plus pi over 2 or minus pi over 2, then if A is 0, then always it maps to itself. But if A is 1, then we want to flip the sign. So pi over 2 will become minus pi over 2, which is just to say add pi. And then likewise vice versa. So to generalize these 2 rules, we would put that with this conditional plus a pi term, which is fine. That doesn't cause any problems. So we've split the rule up into these 2 distinct rules for Clifford's, and that's fine. That all works well until we start looking at the Clifford-T cases. So if the constant part is, say, plus pi over 2, plus pi over 4, and we want to flip the sign conditionally if A is 1, then to flip pi over 4 to minus pi over 4, we're subtracting pi over 2. So we've added this conditional minus a pi over 2 term, which is inconsistent with the phase format that we mentioned, because now we've got these fractional coefficients on our Boolean terms. So why is that a problem? Well, if we're allowing terms like a pi over 2, then by spider fusion, we're also allowing terms like this, and terms with an extra plus c pi over 2, which means that it no longer fits to this this rule that the phase is always, the domain is always 2 opposite points on this wheel. So it could be 4 possible points. So if we're looking at, say, some spider that fits kind of the structure of local complementation, and we're asking, does this rule apply? Then we can no longer say with certainty whether it applies, because this phase could be 0, it could be pi over 2, so we don't know if it applies. Whereas before, even though we didn't know what the phase was, we knew it was at least definitely plus or minus pi over 2. So we can't have these types of phases, because that just causes issues. So what we do essentially is just ignore that, simply. And so we say we've managed to generalize this rule for the Clifford cases, and for the non-Clifford cases, we just ignore it. So if it comes up to, say, pi wanting to commute through a T-gate, we just pretend that there's no way that it can do that, which means that we might be missing out on some simplification that we would be able to do if we were evaluating our parameters at the beginning. But in practice, this doesn't tend to be too problematic. It'll just mean the number of stabilizer terms we end up with ultimately we'll end up with a bit more, but we won't generally end up with, magnitudes more. And then lastly, we've got identity removal. So we know that if the constant part is anything but 0 or pi, this is never going to be applicable. And if it is 0 or pi, then we know that it's only applicable if it's 0. So if it's a pi, we don't know whether it applies. But again, this isn't really a problem, because if it's a pi, then we can just treat it as pi commutation and just kind of keep pushing it to one side. So again, this one we can't really parameterize, but it's not really a big issue for us. So that's all the rules sort of parameterized, which is quite handy, which means that now what we're doing is, instead of simplifying our circuit, reducing it, decomposing it 2 to the n times, we just have to do this once for a parameterized inputs. And then we just have to evaluate this 2 to the n times. And evaluating, in theory, should be quicker than doing this whole reduction. And particularly if we make use of GPU parallelism, which we'll come on to next, this can be quite significantly quicker. So the parameterized scalars that we'll end up with will be some complicated, messy looking string like this. And while this looks very messy, they do all follow some structure. So each term will be of one of these 4 formats. And the overall scalar will map to this structure. So it'll be the sum of a bunch of terms, and each of those terms will be the product of a bunch of these subterms in these forms. So we'll come back to that and just talk about GPU parallelism for a minute. So if we have a bunch of tasks and we're running this on one core, then obviously the runtime is going to be just the sum of the individual runtimes. If we have multiple cores, then we can do them side by side. This is just parallelism in general. And obviously, if we have 4 cores, we can parallelize that further. And for CPU parallelism, this is pretty trivial to do. We can just say divide these tasks up into parts and do them side by side. For GPU parallelism, it's a little bit different, but the main concern for us is the fact, this is bottom rule, the fact that we have this what's called single instruction, multiple data kind of paradigm, where you have to be doing the same function on all the data. So for instance, if you're doing CPU parallelism, you could have all these different cores computing completely different functions. Whereas in GPU parallelism, you get a lot more cores, but they all essentially have to be doing the same function, just to different bits of data. So where this is useful is in cases like this, where you've just got a big chunk of data and you're applying just the same function to it. So in this case, we're just doing some simple arithmetic mapping. So what we're going to use this for is to simplify, to evaluate our parameterized expressions. So we'll just look at the node type terms for now, just to keep things simple. And we'll just consider a very simple example where we have 2 terms. The first one has 2 subterms, and the second one just has 1. And this is the structure, remember. So it could look something like, the first term might look something like this. So it's just a product of 2 of these with different constant parts and different parameterized parts in there. And then the second term might look something like this. And you can see this maps there. So the first thing we want to do is make sure each term has the same number of subterms. So we can just add this dummy term. Just essentially say multiply by 1. And now we can express this in terms of a table. And so each row on this table is one of these subterms. So we can see this orange subterm is this first row, where the first column is saying, is this a real subterm or is it just a dummy for padding, as this one on the right is? And then we're still on the constant. So 2 is because we have 2 over 4. And then because this has the parameters a and b, we just say a and b both have 1, and there's no c and d, so we set those to 0. And so we can express our long-winded scalar parameterized expression just in terms of a table, which is very, very neat and handy structure it. And then a quick aside on how we're storing this in memory is normally you would use what's called row major ordering. So it's kind of the order you read a book. So top left, top right, and then the next row. And this makes sense if you're doing sequential processing on a single CPU, for instance, because it means all the data is together. You're processing this first row as one, so you want all that data to be together. Whereas if we're doing GPU parallelism, we're processing each of these rows in parallel. That's the idea. So the first time step, we're processing this sort of dummy column, and then the second time step, we're processing all the A column, and then all the B column. So we want to group these in what's called column major order. So we're reading downwards through the lines, and that's kind of a subtle point, but it makes quite a significant difference to the runtime, which is something to be aware of. But for practical purposes, we can just consider this as a 2D array. It's just that obviously in memory, this is stored linearly. So we said this is our data for our example node, our example scalar. And then we'll have, likewise, a big table of data for the other subterm type, and then the other two subterm types, they'll each have their own big table of data. So we send this big chunk of data along with some tiny bit of metadata, which just says, how many parameters are there, how many subterms per term, just a few bytes, really. And we send this to the GPU. This can be relatively slow because this might be a few gigabytes worth of data. But once it's on the GPU, every time we want to make a new evaluation, so essentially we're saying we want to set these parameter values and evaluate that, then we're just sending a few bytes. So that's kind of negligible. And then how are we actually evaluating this on the GPU? So remember that each row here is a subterm on which we're trying to process in parallel. So for example, this first subterm is expressed as I've written up the top here. That's what that corresponds to. So the first thing we do is multiply the parameters out. So if we're saying we want to evaluate it given the bit string that A and D are 1 and B and C are 0, then we just multiply this by each row in parallel on different cores. And this essentially has the effect of substituting in these parameters. So we're saying, well, in this first example, A substitute in 1, and for B we substitute in 0. The next step then is to reduce this XOR string. So we just sum them up and mod 2. So this has the effect of turning this 1 XOR 0 into just 1. And then the next term we add on the constant part, so that's fairly straightforward. And now we've got a big list of these subterms, and they all follow the same format. So we just look at this constant part, what's the coefficient here, and there's only 8 possible examples, 0 to 7. So to save us dealing with slow kind of calculations with exponentials and imaginary numbers, we can just use a lookup table, and we can store our complex values such as four numbers. So in this example, the coefficient here is 6, so we just say this maps to this mapping, which is essentially to say we're evaluating this expression and it becomes 1 minus I. And so we're doing that for all these rows in parallel, so it's very efficient, very fast. And then we've got this big string of all of our scalars reduced, and now we just need to multiply them together for each term and then sum together each of the terms. So we can make use of efficient parallelism techniques, since it's already on the GPU, to multiply these and sum them. So instead of summing them kind of one by one with O and N, as you would normally do, we can use one more step of GPU parallelism to kind of speed this up. So just imagine we want to sum together all of these numbers. Instead of going through and adding them all up, we can split them into pairs, and each pair can be on a GPU thread. We just sum each pair. So in the middle here, we sum the 4 and the 5, and we store the output 9 on the left. And then we just repeat this function, but for doubling the size of the threads. So now we're considering blocks of 4, and we're summing this 9 and the 13, and we store the output on the left, and then we repeat and repeat. So this allows us to sum a big list, or to multiply a big list in O of log n. So we apply this in order to multiply together all the subterms within each term. And we can use these relations to avoid us having to do any complex calculations with complex numbers. We just look at the coefficients of the different parts. And then lastly, we just do the same algorithm again, but for summation rather than multiplication in order to sum together all the terms. And then what we're left with is just 4 numbers, which represent our scalar, our complex number. So in this example, we've got these 4 numbers, which represents this scalar. And that's the answer for our, having evaluated our circuit for this particular input bit string. And then we can just return this. So what we're doing is inputting to the GPU the bit string we want to evaluate against. It'll process that very efficiently by parallelized steps, and then it'll just return the answer. And then we give it the next bit string that we want to evaluate, and it'll return the answer, and so on and so forth. And then one more step we can do is called pipelining. So we send the first parameter values that we want to evaluate, and while that's processing, we send the next one ready. So once the first one's finished, it doesn't have to wait for us to send the next one. It can just immediately, it'll have that on the GPU ready to go. So yeah, so that's essentially the idea. And you can see how we can use this for this left-hand side approach of classical simulation, because we've already got these parameters here. For the right-hand side, we can do likewise. And we can just say, for example, suppose we want to do 10 samples, then what's the probability that this first bit is 0? Let's say it's 0.3. Then we would have 3 instances where we want to evaluate this for 0 and 7 for 1. And instead of doing these as 10 independent cases where we're reducing the whole thing every time, we just keep it parameterized and evaluate it for each of these once at the end. And then we do it again for the next step, for the next qubit and the next qubit and so on. And then we gradually build up these 10 outcome bit strings in parallel. So that's how we can use it for that approach as well. If we want to weakly simulate, say, a whole bunch of times for different input bit strings. So what's the runtime of this? So is this all worthwhile, essentially? So if we're just doing one sample, so we want to provide one single input bit string and see what the answer comes out to be, then it's going to be a lot slower to do this method, because this initialization time of sending everything to the GPU, plus it's slightly slower to keep everything parameterized and have all these scalar terms. But once it's on the GPU and all ready to go, every subsequent sample is very quick to do, because we just have to send over a couple of bytes, and it can process this all very efficiently in parallel and just send back a couple bytes, which means as we do more and more samples, you see that the runtime will gradually, this initialization time will gradually become negligible. And it'll be much quicker to use this method versus the normal sequential method. So if we look at a particular example circuit and see just kind of how this fares, this is the speed up factor we get for our method versus just doing this normally in Quizzix, versus the number of samples that we're taking. So again, if we're taking just a few samples, it's going to be slower, and then the more samples we take, okay, that's fine. So in this example case, the terminal speedup is 101. That's what it'll approach to as you take more and more samples. And if we assume then that generally we're going to be taking many thousands or tens of thousands or millions of samples because of this exponential relation, if we're doing, say, 10 qubits, and obviously there's already 2 to the 10 samples that we're taking, then we care more about the terminal speedup. So if we just try this on a whole bunch of random circuits and see what terminal speedups we end up with, these are the results that we get. So if the T count is very small, you don't get much speedup, which makes sense, because particularly if you have fewer terms than you have GPU cores, then you're not really getting full advantage of the GPU parallelism. But these are trivial cases anyway, that we can simulate these in no time, just in the normal method. So beyond the trivial cases, we can see that there's quite a range, but we generally get speedups between sort of 60 times and 100 times, with some outliers that are much quicker and some which are just less effective. So that's quite a nice result. We're getting speed ups, 60 times or 100 times. That's difference between like a day and a matter of minutes to compute these things. And the reason for these big outliers is because we said earlier on that the pi commutation rule applied to T spiders we would just ignore. And in some circuits, it could be very unlucky where we run into these instances where we want to apply pi commutation to a T spider quite early on, which means that we end up with a lot more scalar terms than we would if we had evaluated at the beginning, which explains these lower outliers. And then there are some lucky cases where we kind of never run into this, or very rarely, or just on a couple of branches of the decomposition. But generally, it's kind of somewhere in the middle, and we get this significant speed up. So this is the first paper. So I guess before we move on to the second half, does anyone have any questions about this project?
So you were considering in your benchmark 20 qubit circuits or 36 T gates?
Yes, I believe so. Yeah.
So that's still quite on the small side. Is that just like something you picked in the middle, or is that like about the size that fits on a single GPU? Or if not, like what does fit on a single GPU?
Oh, well, a point on that is, if I go back a few slides. So the GPU, yeah, only has a couple of gigabytes, so we can only store so much. But when we are decomposing, this isn't currently implemented, but what we can do is kind of a depth-first approach. Yeah, so you can see this where we have all these branches, all these terms. We can do a depth-first approach. We can just do kind of the left-hand bunch of branches as one, and then the next batch of bunch of branches, and then the next batch. So if it does exceed the memory capacity of the GPU, then we can just batch it. But this isn't currently implemented. And
but then if you batch it, don't you have to reload the memory on the GPU every time you have to go to like a new variable set? Or
well, what you would do is for the first batch, you'd evaluate that for, say, if you know how many samples you're doing in advance, then you can evaluate that for, say, the first for 10,000 samples and just store those numbers. Do the next batch for the corresponding 10,000 samples and add those to the first 10,000, if that makes sense. So yeah, we do have to load each batch individually, but the time it takes to load the batch becomes negligible if we do lots of samples. Hopefully you see what I mean.
Actually, I have a question about the solving for this Y. So I think you have this like lookup table that you have A, B, C, D. And are those like entries in your unitary matrix?
No,
Yeah,
so
like
these
this
are,
table.
so we have, instead of storing our scalar expressions as, say, 1 plus I or 1 plus root 2I, we could just store it as the coefficient. So we just store what's the constant part, what's the constant coefficient of root 2, what's the coefficient of I, and so on. So this way, we're just storing it as 4 small numbers rather than dealing with, storing root 2s and stuff where we have these long floats or whatever. So it's just a representation of this. It's just a neat way to represent the scalars.
I understand the representation. I'm not sure how this one is related to like this whole like circuit diagram that you showed earlier, and how is it related to the Y value that, like, I think at some point you said there's a lookup table for Y?
I think I know which bit you mean. Let me check.
Yeah,
this part?
one. Yeah.
Yeah, so by the previous step, when we've added all the constants and reduced this, then each row is essentially representing one of these. So it'll be 1 plus e to the I pi something divided by 4. And we just need to pay attention to what that something is. And there's only 8 possible states here. So it can only be 0 through 7 because where we have a resolution of T gates, right? And instead of reducing this to what value this represents by dealing with exponential calculations, we can just use this lookup table to map these 8 possible states, if that makes sense.
And so this is a canonical decomposition, right? Like you only have, given a y, you only have one way to find a, b, c, d.
Yeah, exactly. Yeah.
Right. And how does a, b, c, d correspond to the t count that you're trying to, or it's not related?
So the t count will determine how many terms we end up with, which will be the number of rows that we have here. And for each row, we want to map it according to this lookup table.
Right.
Mm-hmm.
Thank you.
Okay. Do we have any more questions, or shall I move on to the second part? Okay, we'll go on to the second part then. So in the similar vein of classical simulation, there's a second kind of method that we have. So I mentioned earlier on the BSS decomposition, which is this one that relates 6 t-spiders to a sum of 7 terms. There are new, better decompositions than this out. So for instance, this one has a slightly better alpha. Alpha, by the way, is how efficient the decomposition is. So lower alpha is better. It just means that given a t count t, then we'll end up with 2 to the alpha t terms. Yeah, so we have this example, which relates, what's that, 5 t gates to 3 terms. And then these are other ones which are known, and these are called cat states, but these require like sort of specific structures where we're looking at, for instance, this top one, it needs a Clifford spider connected to 6 T-like spiders. And these have better decomposition efficiencies, but these are a bit more specific. You need to find these structures. But I'm going to focus on sort of the simplest decomposition of all, which is just to exchange one type of spider for another type of spider. So we're changing Z type to X type and vice versa. And so that looks like this. So you can imagine if the spider there is pi over 4 T-like, then we're removing one T-gate in exchange for getting 2 terms. So this has a pretty bad alpha of 1. But despite this bad alpha, of this apparently bad alpha, there are cases where this is actually very useful. So imagine we have these 2 T-like spiders sandwiching a C-knot. We decompose this top part. Then we'll end up with something like this. So that didn't seem to help. We didn't reduce any T count. However, if we now look at these 2 individual terms, we can see that we are now able to reduce them to Clifford. So we can, yeah, so immediately alpha is infinity because we haven't removed any T count. But if we start simplifying these, we see that both become Clifford, which means that applying that decomposition to a completely different spider has allowed us to fuse these 2 T-gates in both branches. So in this case, alpha will be 0.5. And you can imagine if the vertex that we cut as well was also T-like, then that would be even better, and alpha would be 1/3 here. And this is kind of the jumping off point that we're going to work with. So imagine we have one of these sort of T, C not T sandwiches, and there's another one next to it. Well, we can fuse the heads of the C knots and then decompose, just cut that vertex. And again, we'll be able to fuse the top 2 pair, and we'll be able to fuse the bottom 2 pair. And we're still just cost us 1 cut. So now alpha is 0.25. And you can imagine we could have 3 of these sandwiches, or 4 or 5 or 50 in theory, which means we could still just do 1 cut and we could be removing potentially hundreds of T-gates. So this much is already kind of known about. It's not formulated quite in this way, but in Julian Cody's thesis, he does kind of a similar thing. And he finds that on certain real-world circuits, there are instances where just applying 1 cut via this kind of means allows, I think, 300-something T-gates to decompose, to disappear, which has an alpha of like 0.003. So that's kind of the best case scenario. But we're going to take this a step further. So consider this example ZX diagram. You can identify right there is one of these T, C not T sandwiches. So if we were to decompose vertex 2, then these 2 T spiders would disappear in exchange for getting 2 terms. We can identify there's quite a bunch of these instances here, but there are some overlap. So if we were to decompose this blue one on the left, then it's sort of mutually exclusive with this red one because they're sharing a T spider. So which ones do we want to cut, essentially? Which ones do we want to be decomposed? Well, one method, we could recognize these three, which means that with 3 cuts, so 2 to the 3 terms, we'd be removing 6 T gates. Or we could consider these 4, and now with 4 cuts, we'd be removing all 8 T gates, which would give us an alpha of 0.5. Yeah, so these would be the 4 we would cut in that case. But consider instead we cut this vertex, which might seem kind of a strange thing to do because it doesn't, it's not blocking any T gates from fusing with each other. But suppose we do cut this one, then we end up with 2 terms that look like this. And in the case of the first term where A is 0, these spiders in the middle would just disappear by identity removal. And in the case that it's 1, so these are all pi, we can just push them all to one side via pi commutation. So essentially, we just kind of push them like that. Which means now each of these sandwiches that we identified, these C knots, can fuse together. And now we can decompose them as one. And from what we said a few slides ago, each of these pairs will now be able to reduce to Clifford, which means in this case, we would have alpha is 0.25. So we've just done 2 cuts, but we've removed all 8 T gates. So that's kind of the broad goal here, is that we're looking at a structure like this and we're asking ourselves, which one should we be cutting to try and kind of maximize our efficiency here? And perhaps counterintuitively, it's better to cut certain vertices that aren't immediately going to help, but will allow us to fuse other vertices that decomposing would help. So instead of cutting vertices 2, 6, 11, and 15, we can cut 8 first, and then it'll allow these 4 to fuse, and then we can cut them as one. So it seems we want to know which ones to cut and in which order. However, there is a slight analysis we could do to kind of correct for an inefficient ordering. So this is the decomposition that we said, so we can parameterize this just like this, quite straightforward. And suppose we do decompose vertices 2, 6, 11, and 15 first, and then we do 8 last. Then firstly we end up with this, and then decomposing this top one brings us to this. So now we've got 5 parameters. So that would be 2 to the 5 terms, but we're keeping it parameterized for now, so we're just looking at 1. And what we can recognize is, remember this scalar relation from the beginning, which we can simplify for the Boolean case to be this. And if we look at this left phase node here, where we have a plus b plus e times pi, we recognize that this will either be 2 or 0, depending on what this parameter string evaluates to. And if it does come out to be 0, then obviously multiplying this graph by 0 means the entire graph goes to 0. So of these 2 to the 5 graphs that we have, these 32 graphs, many of them will be 0. And if we can discount those without having to check through each one, then that would be quite handy. So essentially we want to ignore the cases where it's 0 and just focus on the cases where this is going to be 1, which means we need this bit string to be 0, which we can rearrange, and it tells us A equals B XOR E. And then we repeat this idea for these other 2 nodes that we have. And now all of our parameters are in terms of D and E. So we've reduced our 5 parameters down to 2 parameters, which is back how we started. So essentially what we've said here is, if we do cut this in an inefficient order, so we do 2, 6, 11, and then 15, and then we do 8 last, we can correct for this just by some analysis to have the same effect of cutting the 8 first and then fusing and then cutting. So then lastly, we want to talk about the heuristic that we're going to use to try and find where are the optimal places for cutting. Well, there's one more thing to consider, which is if I add this extra C knot on the left here, you can see that these 2 spiders, we want to be able to fuse those. But to fuse them, we need to cut not just 1 vertex, but 2 vertices. So how do we know if it's worthwhile cutting these? Because it gets a bit more complicated now. So we'll get to that and just kind of run through the procedure on this example. So for each of these C knots that are blocking T gates from fusing, we'll give it a weight of 2. 2 meaning that if we were to cut this, it would allow 2 T gates to fuse together and cancel out. So we'll set all of those, and this is the bottom tier. And then on the next tier up, we'll be looking down at the previous tier, and it'll be halving all of their weights. Because now, instead of just considering how worthwhile is it to cut this one, we're also cutting the parent as well. So we're doubling the number of terms we're going to get, so we halve the weight. And we also cap it between 0 and 1. So we have kind of this normalized range, which kind of says if it's 1, then it's very likely that this will be a worthwhile cut, and if it's 0, it's very unlikely. And then obviously anywhere in between. Yeah, so now we're looking at vertices that are blocking weighted vertices from fusing, weighted vertices from the previous tier. So this one, for instance, is blocking these two, highlighted in green, from fusing to each other. But there are actually, so we'll have, they have a collective weight of 2, so we'll sum their weight to 2. But there are actually 2 vertices that we need to cut in order for these to fuse. So we'll divide by 2. And this gives us a weight of 1 for this vertex. And then likewise, if we look at vertex 20, we can see if we were to cut this vertex, there would be a total weight of 3 that would be able to fuse together. So 3 divided by 1. And then there's this one over here, which would be able to fuse with the rest. So it has a weight of 1, but it would only be able to fuse with the rest if we were to be cutting 2 parent nodes. So we'll do 1 divided by 2. And so this gives us a weight of 3.5. So we'll just assign that weight to this vertex. And then we just repeat this process for higher tiers. But before we do that, we restore the previous tier to their actual values as opposed to the halved values. And we look at the next tier up. And in this case, we'll find there are no vertices that are stopping the tier 1 vertices from fusing. So we essentially say, okay, we're done. And these are our weights. And so we look at the highest tier, which in this case is 1. And we look at the highest weight in that tier. So in this case, it's 3.5, which means that this vertex 20 is the highest priority. This is the most worthwhile cut. So if we're going to be cutting any vertices, that should be the one we start with. And then once we have this list, the rest of it is fairly straightforward. We can just say, okay, cut that vertex. And then we end up with these 2 terms, and we simplify those terms, and then we just kind of repeat the process to figure out the next vertex to cut in each case. Yeah, and that's broadly the heuristic approach that we're using. And you can imagine if we did have some T phases on these vertices, then we add an extra 1 to the weights, but we keep these in brackets because these weights are only relevant if we're considering which ones we're cutting. When the higher tiers are looking down and they halve the weights, they don't account for this +1 because it's not relevant to that case. But all this means is if we're going to cut this, it has the weight of whatever the weight is, plus obviously it's going to be removing 1 extra T gate if we cut this. And then lastly, if we had some instances where some T gates could fuse, then this vertex 20 would have some weight for the lower tier. But then it's also stopping 2 lower tier weights from fusing. So it has a weighting for the higher tier. So this vertex 20 has 2 different weights for 2 different tiers. And that's not a problem. We can just keep that as is and just carry on the process just as normal. That doesn't cause us any issues. And so broadly, this is the approach that we use. And we want to test this out on a bunch of random graphs, essentially. So we don't use, so this isn't particularly helpful on completely random graphs if you just randomly stitching together spiders, because it relies on structure, the structure you would get in actual circuits. So we generate our random graphs with some inherent local structure. We don't embed large structures because it's kind of cheating. But we just do some local structures. So for instance, using Toffoli gates, because these have a lot of these kind of structures in them, and these kind of T, C naught T groupings just on random qubits to place those around. For very small circuits, we can verify manually. We can check every possible combination of vertex cuts to see which one was the best. Obviously, we can only do this if the number of vertices is very small, say like 10 or 15 or something, because you're going to be doing 2 to the number of vertices checks on your brute force. But for these very small circuits, much smaller than the one I'm showing here, we can check, does our approach find the most optimal result? And we found that about 70% of the time it did. However, it's worth noting that as we scale up to much larger circuits, it's very unlikely that we're still going to have that kind of success rate. But the main point really is that even in the cases where it didn't find the most optimal, it still found an optimal solution, so somewhere fairly close to the most optimal. Because obviously to find the most optimal reliably, you'd have to use some kind of brute force method, which would just be exponentially slow. So we tried this on a whole bunch of much larger random circuits, and these are the results we observed. So comparing against the BSS decomposition, we can see that the number of stabilizer terms we end up with is much smaller. And you can see the trend is quite clear here. The x's is just an estimate of the number of terms we're going to get, whereas the solid circles are the actual numbers that we got. So the estimate is just to say, imagine we don't do any simplification. Can we predict how many terms we're going to get? So in terms of BSS, that's just taking alpha as 0.47 and just extrapolating from that. But the circles are the actual measurements that we took. And you can see that quite reliably, it's sort of magnitudes quicker to use this approach. And another way we can formulate these results, instead of looking at the number of terms, we can translate that to the effective alpha. So how many terms will we be able to remove versus, sorry, how many T-gates will we be able to remove versus the number of stabilizer terms we ended up with. And this is what we end up with. So as BSS in theory has an alpha of about 0.47, in practice, because of the interstep simplification, it's a bit closer to 0.4 or 0.35, something like that. Whereas our method has a lot more fluctuation, which is expected because obviously this is a heuristic approach, but the alpha quite reliably is much lower. It's often between 0.1 and 0.2. And this is kind of the idea of this second approach. So overall, I've kind of shown here, we have kind of two methods of speeding up classical simulation. The first one is parameterizing, so we're reducing some redundancy and we get this linear speed up. And in the second case, we're looking at, instead of just picking the most optimal, what is apparently the most optimal decompositions, we consider these less efficient decompositions, but analyze the whole structure. So we don't just take their alpha in the immediate vicinity, but how it allows the graphs to simplify overall. So these are the two approaches we've got, and that concludes my talk. So if you have any questions, please ask.
Right. Thank you very much, Matthew. You can thank our speaker using the little clappy emoji thing on Zoom. Or do it in real life. I might. All right. Do we have any questions from Matthew?
Yeah, I have a question. Thank you for the talk. It's very interesting. I wonder if, so suppose you have a circuit that is represented in terms of like the C0 and the pi over 4 gate, as you show in this example, then there's no unique way to present it, right? You can massage the circuit and then you can place things in a different location. So have you investigate how the original placement of the diagram like this would affect the synthesis, like, or like the T count reduction?
Yeah, I know what you mean. That's a very good point. I didn't really have the time to go into that here, but yeah, obviously I've kept this kind of in this graph-like form, whereas normally you'd reduce this to some kind of, sorry, I've kept this in circuit-like form. Normally you'd reduce it into graph-like form where everything is just green and connected by Hadamard edges. I find that if we fully reduce it to that kind of graph-like form, it's a lot harder to kind of find these instances. So the method I'm using is sort of a partial simplification, where we do as much fusion as you can possibly do. You any pi phases, you try and push them all to one side, and those are really kind of the two main steps when we try and keep everything in this circuit-like form. So we might be missing out on, in a lot of cases, on some simplification, but by keeping it in this graph-like form where we've just done some partial simplification, then it makes it a lot easier for us to track where these weights should go and where they should be. But certainly there's some scope to kind of figure out how this would translate for more of a graph-like structure. But yeah, it's just kind of a choice we've made, is just to stick with the circuit-like approach, because then it's much easier to track these and to keep everything structured. Because we don't want to lose that structure, otherwise we're kind of missing out.
So for example, if I push all the pi over 4 gate to one side of the circuit, or like one side of the diagram, and then the other side of the diagram would be the Clifford component, then the method of the cutting would no longer works because it no longer have it no longer satisfy the formula that you presented earlier.
Yeah, exactly. So so that's why we don't do kind of a full simplification, because then we lose a lot of the structure. So in order to try and maintain as much structure as possible, we just do some basic steps of fusing as much as you can, pushing pi gates off to one side. So yeah, the reason we don't do this full decomposition is, as you say, we don't want to lose that structure.
Oh.
But then, of course, it is kind of that in itself is also kind of a heuristic to how we're keeping the structure, how we're going about that. But we just use a very simple approach and essentially just keep it in circuit-like form.
Thank you.
You're welcome.
Okay, any other questions? Okay, then so in describing the results of your first paper, the rewrites you showed, this didn't involve a phase gadget fusion. Is that
no, you're right, it didn't.
Is that like because you sort of assume these things are pre-optimized, so everything that can be fused is already fused, so it doesn't make sense to do phase gadget fusion?
I guess it might be worth trying to consider generalizing that one. It's been a while since I've kind of looked into this, but we kind of found that this method seemed to work very well, but I can't quite remember how effective it was, or if we were able to parameterize the gadget rule. But it didn't seem to be particularly pressing.
Because my original intuition for why the simulation method should work better is because when you interleave the decomposition with optimization, this intermediate optimization could cancel additional T gates, and like the way you cancel T gates is spider fusion and phase gadget fusion.
We mostly rely on the two derived rules, which these two. So we're mostly using these two rules. I think it is still using the gadget fusion, but it's not parameterized. So it'll only use it in cases where there's no parameters involved in that area. So essentially what we've done is taken the code for physics and just added accounting for these parameters. So we haven't rebuilt it from scratch. So if the gadget fusion is already in there, then it'll still be in there, just not parameterized. So we will be missing out on some degree of simplification, but as we find in the results that generally we don't miss out on much. So I don't have the raw data with me now, but we did find that usually the number of terms we get, if we keep it parameterized versus evaluating at the beginning, is sort of slightly more, maybe like 1.5 times more. And only in very rare cases is it like 4 or 5, 10 times more. So yeah, maybe that could be improved even slightly further, but it didn't make it wasn't a big issue for us.
And in your second paper, you were considering these decomposed Toffoli circuits. Is that correct? Like that's the way you were placing these way in a structured way?
When we were generating our random graphs, we were generating them with Toffoli's and C-knots and things, yeah, because Toffoli's have a lot of these structures in.
So you place Toffoli's and C-knots in between, and then some more Toffoli's, like this kind of stuff.
Yeah, just kind of random qubits. Yeah.
So like a Toffoli gate can be decomposed into Clifford using just 2 terms. So this would decompose 7 T gates into 2 if you were to consider that metric.
Yeah, and likewise, this method should find the cuts that would allow it to split into 2. And if you have multiple fusing together, it would still just split into 2. Yeah.
So is that because you were comparing against the BSS decomposition, if you sort of draw the line of like the efficiency of 7 into 2, where would this line be? Like would your method still be below that?
So if we just take the efficiency to be the 7 over 2, yeah, I guess we could map what the alpha would be for that, but the random graphs aren't just Toffoli's. There's also random T gates in there and random C-knots. So it wouldn't really make much sense, I think, to just assume that every 7 is being replaced with 2, because it's not just Toffoli's.
Yeah, so the 7 to the alpha would be 35, like 0.35, I think. 0.36.
0.25.
So, yeah. 336, if I'm not mistaken.
0.36.
Yeah, because okay, so 2 into 8 would be like 1/3, and this is 2 into 7, so this should I don't maybe calculate it wrong. I just tried to calculate just now. So, yeah, I think your method would be still be better.
Well, since we're here, can I ask? So just now you said the number of stabilizer terms is related to the T count. Like, sorry, what do you mean? Like, in terms of interpreting the x-axis and the y-axis in this diagram?
Yeah, so if I just run back to the decomposition. So, well, we said we run into this kind of graph when we try and simplify Clifford+T, and we use some decomposition to replace these T gates with a sum of terms. So if we're using this decomposition, then we replace every 6 T gates with 7 terms, and then in each of those we replace 6 more with 7. So this grows exponentially with the number of T gates. So we end up with a big sum of terms, which grows with 2 to the alpha T for T gates. So that's why we end up with huge amounts of terms in relation to relatively small alphas. And so that's what we're representing here. So on the left one, for instance, we're seeing what exactly is this relation? How steeply does this exponentially grow with the number of T gates?
But I thought the stabilizer terms are related to the are related to the Clifford component. How I didn't get why stabilizer terms is related to the T count.
So the stabilizer terms, they themselves are about a sum of Clifford terms, but the number of them we get is determined by the T count, because we are splitting our graph into. So say we use the very simple decomposition of this one. It means for every T gate that we get, we're splitting our graph into, we're doubling the number of terms we have, the number of graphs, and then we keep doubling it for every T gate, right? So if we have 10 T gates, then we end up with 2 to the 10 graphs by this method. So that's why the number of terms you end up with is related exponentially with the T count.
And what if you change the face of pi over 4 to pi over 2 to the power of something? So essentially you're considering the Clifford cyclotomic gate set instead of just Clifford+T. Does your method still apply?
So if instead of expressing this as pi over 4, we would express it as what?
Pi over 2 to the power of something, 2 to the power of m, where m is a positive integer.
That might be a better question for John, actually, but as far as I'm aware, I don't think that the rewrite rules would still kind of work in the way that they currently do.
So this decomposition still works, right? You just replace the pi over 4 with pi over 8 or pi over 16 or whatever.
Yeah.
So this would all still work. But your tricks for when you said essentially, okay, we can parameterize these rewrite rules, but we just ignore the cases where it's not Clifford. So that means you start to ignore more and more stuff once you get to smaller and smaller faces. And the other thing is that you don't really have nice stabilized decompositions if your faces are not pi over 4. Is my intuition that if you have pi over 8, pi over 16, you have like less nice stabilized decompositions.
Yeah. So it's very lucky that so that rule we pointed out at the beginning where we said the phase is always separated by pi. So we always know, even though we don't know what the phase is, we know it's either C or C plus pi. It's very lucky that in almost all the cases of the rewrite rules, that allows us to parameterize them even for Clifford+T, with the exception of pi commutation and identity removal. So as you say, if we were considering more arbitrary phases, so pi's over 8 or pi's over 16, then yeah, this would pretty much, it would be unable to simplify in any meaningfully parameterized way.
And of course, your representation in the GPU code would use more data, which I could like be bigger because you need to like.
Yeah, we'd end up with a lot more terms, so we have a lot more rows. This is very much geared towards Clifford+T. So I don't think if we increase the resolution to pi over 8, so it's 16, I don't think it would be particularly helpful.
But what if we go to that table that you said there's a one-to-one correspondence between y and a, b, c, d, and before you said a, b, c, d are the integers, but what if so let's say if we go from pi over 4 to pi over 8, now instead of letting a, b, c, d being in the integer, now we let a, b, c, d to be in extension of z with I. So it's a Gaussian integer.
So instead of it being an integer over 4, we could have 0 to 15 over 8, that kind of thing. So we increase the resolution.
The table would just become bigger, is the answer, I think.
Yeah, so we could just double this mapping. But I think the real problem is that we would be missing out on a lot of simplification, so that the number of rows that we get in the data to process in parallel, which is the number of terms, would be much greater. I think that's the real downside of having a greater resolution in our diagrams.
What do you mean by resolution?
I mean, so at the moment we're just considering all the phases have to be multiples of pi over 4. So that's the Clifford+T regime. But if we increased it so it could be, say, pi over 8 or pi over 16, that's what I mean by increasing the resolution.
Oh, okay. Thanks.
But I just I calculated the alpha for this like Toffoli decomposition wrong. If you would consider a Toffoli to be like 7 T gates, and then this is like a specific configuration that decomposes 7 into 2 terms, that's like the alpha is 1 over 7, so that's 0.14. So that's like right in the middle of like what you find for your thing as well.
But that would only be applicable if the graph is made entirely of Toffolis, though, right?
Yeah. So then you would be looking for like patterns that are Toffoli gates, or like Toffoli gates maybe with surrounded by infinals or whatever. But,
so this method should, for every Toffoli gate, it should just split those 7 T gates into 2 terms anyway. But these graphs are made from more than just Toffolis. It's also just like random T gates placed around and whatnot.
Okay. Yeah. Right. Okay. In what language did you make the GPU stuff? Is it CUDA?
Yeah, CUDA. Yeah. So that
Python and CUDA.
So all the all the parameterized stuff is done in Python, and then that all gets split into C++ and then into CUDA. Yeah.
Is that as horrible as I think it is, or is it not that bad?
What's that?
Is that as horrible to write as I think it is, or was it not that bad?
CUDA. It's a different way of thinking about things, but I quite enjoy it. Like language-wise, it's just C, but you've kind of got to get your head around running things side by side rather than one after the other, and you need to avoid loops and if statements. It's just kind of a different way of thinking, but yeah, it's not too bad.
Yeah, and the age of ZX on GPUs is upon us now.
Yeah.
An idea that's been floating around for a long time now, I think. So, yeah.
Yeah, this is I don't think I mentioned it, but this is all running on my laptop GPU. So I think if we tested this on Alex's fancy new GPU, then it would be even quicker.
May I ask, like when you're having this like tier 0 to 2 heuristics, what if you like design some kind of like reward function and let the deep reinforcement learning to make the decision? Do you think this would be?
Well, it's funny you mentioned that actually, because Aleks Kissinger, who's in the chat with us, is in the call, and Richie and I, the three of us are doing essentially just that. So we are trying to train a reinforcement model to find where are these optimal cuts. That's the current project that we're working on. So instead of relying on this heuristic.
Have you discovered like the one that is given to you by like machine learning is actually very counterintuitive to humans' choice?
We're kind of really at the early stages right now, so we don't really have much to point to. But possibly we'll see. Because there's more than just fusing T gates in this sense. There's also kind of like a handful of ways we can remove T gates. So this could find some very kind of esoteric cuts that we wouldn't even think to consider. But yeah, hopefully that this machine learning approach might prove more effective than this heuristic. That's the hope.
Like these AI Go players that make a move and then like 10 moves later turns out to be like amazing for this reason. Like you make a cut And
Yeah. The
10 layers deep, you discover, oh, because then this is connected.
Yeah, I mean, it really is just you can't really kind of predict why they're doing certain things, but I mean that's kind of the benefit, right? So if we were to design a heuristic that was like super clever, it would be kind of impossible to figure out all the intricacies, whereas the machine learning approach hopefully can just kind of figure this out on its own.